In this video, we are going to start our discussion of section 2.3, which are first order linear equations. There is a method to this. It is very brilliant. Somebody came up with this. It's very interesting. So it's not extremely intuitive. There is a way to look at it, and I will do a video showing where it came from. But up front, I'm going to show a method for this type of equation without explaining where it comes from, because I feel like that's the best way to introduce it. Okay, so let's start off with a first order diffeq. So notice here in the blue box, we have this first order linear. We know it's first order because the first derivative is the biggest derivative, right? That's our order. We know it's linear because I have that dy dx, and then I also have this y here. Counting down, I have no like y to the third, I have no square root of y, I don't have e to the y, I don't have sine y. Those are my only y's. And then the coefficients out front, a sub 1, a sub naught, 0 there, those are just functions of x, also with g of x. So here are a couple examples of a first order linear DE. Notice that first derivative is the biggest one with y. There are no other y's. The first derivative and y. Everything else is a function of x out front. So we're good. So that is a first order linear. Now to solve for one of these, we are going to want to put it in a certain form. It's called general form of your first order linear ODE. All they did is you just want to get the first derivative out front by itself. This p of x here that they have is just whatever was there divided by the number that was out here. And I'll show you what I mean. The thing is about a first order DE, if we have this standard form here and we're working with that, if f of x on this side is 0, then we actually have a separable equation. So if you ever have a first order DE, and the right side is a 0, you can do it by the separable method. We always want to use that because it's faster, it's easier, and a little more straightforward than the method I am about to show you. Okay, so a lot of students, what they'll try here is they'll start trying to anti-differentiate right away, right? They'll try to take maybe the integral of both sides, but I would have to take the integral of this and this, but I don't know what px is, right? We can't do that at the moment, and that's going to be pretty difficult to do. Potentially. Oh, and we actually really can't even do it because we don't know what y is. I can't take the integral of y because remember the whole point of this is I want to find y. I want to find that function y that solves this equation. So it doesn't make sense to try to take the integral of both sides because I don't know what that y is. So there's a method that came up, and it was a dude from the Bernoulli family. That came up with this is pretty brilliant. It feels like it's out of nowhere. But what they're going to do is they're going to come up with this number based on the function given, the equation given, come up with a number, and it's called the integrating factor. They're going to take this function and multiply both sides of the equation, and it's going to make it easier for us to solve our DE. So I'm going to lay out this method. And I'm going to do it step by step. I would encourage you to do a lot of these. They do get fairly simple after a while. But I know out front for me, it was a lot of work up front. So the integrating factor that they're going to do, or we're going to use, and I'll show this in another video on why this comes up, but it's e to the integral of px dx. Px, remember, is this like number in front of y, or expression in front of y rather. So it's pretty brilliant because we take our integral of that, we get that e, we multiply our function, and the dE actually works out. So let's, I have a method lined out here. I don't like reading this off before we do a problem because I feel like it doesn't mean anything. So I'll leave that there. I'm not going to read through it. There's the method spelled out for you. All right, so let's take a look at an example. All right, so notice right now it is, we have to identify, is it first order or linear first? Okay, so I got dy dx and a y. And notice there are no other y's, right? Y is not taken to the 8th power or square root or weird. It's literally just y and its derivative. The numbers out front are x's. Now, the method above, and I mentioned this, we want it in standard general form. So we don't want that x there. So I'm going to divide everything by x. So I get dy dx plus 3 over x. I keep that y by itself. And then we get x e to the negative 2x. We need to identify what they called p. P was the number that was in front of our y. So that is this number right here. So we're going to find what they call mu. It's a Greek letter. It looks like that. All right, let me show you a type of that right here. That's mu. All right, and how we find mu of x, is e to the integral of px dx. Px being what's highlighted right above. So we get e to the 3 over x dx, and we have to work that out. All right, 3 over x, the 3 comes out, I get 1 over x. So this gets me 3 ln of x, and we want absolute value there. For this problem, we are going to assume x is greater than 0, just to help us out, because we're trying to learn a method. So that means I can drop the absolute value. Now, I don't know if you remember this log rule. If I have a number out front, this is the same thing as taking that number and putting it as a power up there. So that 3 can actually go up, and I'm going to drop the absolute value, x to the third. The e and ln, the reason we did that, now we can actually cancel the e and ln. Those are inverse operations, so they undo each other, and we get mu to equal x to the third. All right, so we have x to the third here. We're going to multiply both sides. Leave yourself some room. If you didn't leave a lot of room, maybe put this off to the side. I'm probably going to have to add a page. So do what you need to adjust to that. I'm going to take now, so what we did, let's recap. Put it in standard form, right, or in general form. That means dy dx up front has a 1 in front, nothing else. We identified px, which is what I highlighted in green there. Let me erase those. That was p of x. That goes right here. So that went there. Then I did the integral, worked it out. Now I have mu. Now why I want mu is I'm going to multiply my dE, this dE, by x to the third. So I get x to the third dy dx plus, okay, I multiply x to the third. I get 3x squared times y. And then I get x to the fourth nope, I think, oh, there was a mistake way back up here. So this mistake happened right here. It was supposed to be over x. Not a bad fix. We divided everything by x. Some of you guys probably caught it way back then. So this is e to the negative 2x over x. There we go. I'm sorry that I want to change it. Thankfully, it's just that 1. Okay, so when I multiplied that, I was checking my notes, and I was like, I didn't get that. Okay, so now I'm multiplying. Let's go back. We are multiplying by this x to the third. I multiplied this equation here, the left side, by x to the third. Now I'm just multiplying this side by x to the third, which gets me x squared, e to the negative 2x. All right, so we found our mu. We multiplied both sides of our dE by our mu. The reason we do this, and this is where students struggle, so bear with me. I'm going to make this a bit smaller, is the left side is going to turn out to be something that we want. Right? The left side, there we go, finally. That left side ends up being the derivative of our mu times y. That is that left side. I want you to check that. So it's a product rule, right? So if I take the derivative of y, first I get x to the third dy dx. I don't know what y is, so that's all I can do. Now if I take the derivative of x cubed, I get 3x squared times y. It's a product rule. We forced a product rule to happen. It happens every single time. That's why this method is pretty brilliant, is because we are multiplying by a number that causes us to have a product rule. The right-hand side didn't change at all. All I did was recognize that it's a product rule. Now, maybe you're asking, well, who cares? Cool. What does that do for us? Well, now if I take the integral, and remember, derivatives and integrals are inverse operations, which means they undo each other. Right? So what I get on the left-hand side is I just get x cubed times y. But on the right-hand side, I'm going to have to take that integral. Now, you're going to hate this. This would be an integration by parts or something called tabular integration. Right? If you need to look that up, please look it up. So what we do is we have sine, we do a sine, we do a derivative, and we do an integral. What we want with the sine is we just do plus, minus, and we just continue that pattern. For the derivative, we want something that's going to go to 0, right? That was the whole point with integration by parts, is we're going to get rid of one of the complicated functions. So I'm going to let x squared go there, and I'm choosing out of here, right? Just like integration by parts, I'm going to choose x squared because I know that x squared goes away pretty quick. Meaning, okay, I take a derivative, x squared, I get 2x, then I get 2, then I get 0. So I don't even need this plus down here. That tells me when I need to stop. The reason I didn't use e to the negative 2x is because it will never get me a 0 integral or derivative. If I take the integral of that, I get negative 1/2 e to the negative 2x. I'm just working backwards. Then I get a positive 1 over 4 e to the negative 2x. And then I get a negative 1 over 8 e to the negative 2x. Just taking the integral, and I recognize the pattern that I'm going to just keep putting a negative 1/2 out front. That's all it is. Now, the tabular integration, if you're not comfortable with this and you want to use integration by parts, kudos. I'm actually just has been recently sold on tabular. So how we figure that out is we take the sign and then we multiply here. So I'm going to write that down. All right, so I got negative x squared over 2 e to the negative 2x. All right, and then I go back to my table, and now I do this way. So I got negative 2x, negative, and it's going to be 2x times 1/4, so that's x over 2, and then e to the negative 2x. Keep going in this manner. Multiply plus times 2 times negative 1/8. All right, so we get 2 over 8 is a fourth, so minus 1 over 4 e to the negative 2x, and then we get a plus c. I wouldn't keep going because if I keep going here, minus 0 times, there's nothing else to multiply by anyway. So there we go. That's how you use tabular integration. I actually really like it. I was not shown this, I don't feel like, or it was in passing. My instructor didn't care for it. So I actually learned that later in life. I really do like it. It's nice. All right, so we are down to a solution. This is our implicit solution. Implicit. To get explicit, I multiply x to the negative 3, and I'm just going to literally do this, like put it on the outside and leave it alone. Why not, right? We want to do the least amount of work as possible, and in that case, we could even pull out that 2x, negative 2x, if we wanted to. There we go. This is our explicit. All right, so let's recap real quick. The worst part about this method, I think, is the integration. The tabular thing will help you out. All right, so let's look here. So first thing we did, let's get rid of some of this outlining work, is we put our DE in general form by dividing by x. So we divided everything by x. Then we wanted to find what is called our integrating factor. Our integrating factor is this mu. So we found that by using the formula, e to the integral of the coefficient in front of y, p of x, dx. We solved that, we got this. Then we multiplied by mu. Maybe we should say multiply dE by mu. We did that. That's what this line is. Then this is a product rule. We forced the product rule to happen. The reason we want the product rule is because once we have the product rule, if we take the integral both sides, it just undoes that derivative, leaving me with the y, which is what we were wanting. Like I said, most of the work is going to be right here. Going to be that integral on the right-hand side. I encourage you to do a bunch of these problems. I will do a few more for examples, but really this is all about repetition. It's all about getting reps under your belt. We're going to use this method a lot because it's one of the early ones. So remember, it works just like algebra. Remember, if I solve a quadratic and I factor it, then I solve linear equations to solve my solution. It's the same way. We're going to use a method, and then we're going to have to use this method because it's the simpler one to solve. So get some reps, do some practice problems.